Okay, hello everybody. Welcome to another installment of Mr. Hewitt Does Some Math, and hopefully you're finding these videos helpful. Today we're going to be looking at some examples of solving trig equations, and this is a variety of different things that you could run into, like in this homework assignment. The first problem that we're going to take a look at is a problem that has frequency. Now remember, frequency is this number right here that's showing up in between your trig function and the x. And right now we have no way of getting that 5 out of there. Dividing by 5 will not help you get rid of this. So what we have to do is try to isolate this entire trig function by moving the 3 over to the other side. So I'm going to start by subtracting both sides, 3 from both sides. And then, of course, I will divide both sides by 3 to get rid of the 3 that's out in front. So we have tangent of 5x is equal to -1. Still, at this point, there's not a way to get that 5 out of there. Dividing by 5 does not get it out of there, so we have to wait. The next thing you're going to want to do is make yourself a chart of where things are positive and negative, and we're looking for a tangent that's negative. That's not going to be quadrant 1 or 3, so we're talking about having an answer in quadrant 2, and also talking about having an answer in quadrant 4. So those are where my answers are going to come from, quadrant 2 and quadrant 4. And now when I look at the number right here, 1, we recall that the reference angle for having a tangent of 1 is 45 degrees. So I want to be 45 degrees away from the x-axis in quadrant 2, that's 135 degrees, and 45 degrees away from the x-axis in quadrant 4 would be 315. So 135 degrees and 315 degrees. Well, if we look back to the original question, we notice that this problem has no limits. So they don't want you to stop looking. And we know that every time we go around the unit circle, we're going to keep coming back to hitting these places over and over again. And the separation between one answer and the next is going to be a full rotation. So in degrees, what we want to do is add multiples of a full rotation onto this, which is n 360. So our final answers to this problem are 135 degrees plus any multiple of 360 added or subtracted on there. N could be positive or negative. So that could be adding or subtracting multiples of rotations, and 315 with multiples of rotations added on. This is the answer for our first problem. Next, we're going to take a look at a problem where you're going to have to use the quadratic formula to help you. Now, you could try factoring this if you want to with that leading coefficient. This is set up like a quadratic. We have a sine squared, we have a sine to the first power, and then we have a constant out here. So because it looks like a quadratic, you should factor it like a quadratic. And the factoring technique here that you'd have to use would be the AC method, where you multiply the 12 with the 3, but then you have to think of two numbers that multiply together to make 36 and add together to make -13. If that's too challenging for you, we can also do the quadratic formula. So x equals -b plus and minus the square root of b squared minus 4 times a times c, all divided by 2a. The thing is, this problem is not a normal quadratic, so what we're seeing here are not x squared and x. We're seeing sine squared of x and sine of x. So when you're doing the quadratic formula, you'd actually be finding the sine of x. So let's go ahead now and plug all the numbers in the appropriate spots. Our b value here is -13, so we're going to get 13 plus and minus the square root of -13 squared is 169 minus 4 times a, which is 12, times c, which is 3. And all of that's going to get divided by 2 times a, which is going to be 24. So the sine of the angles that we're looking for are going to be 13 plus or minus. The math inside of here, 4 times 12 times 3 is 144. And when you subtract that from 169, you're getting 25. And the square root of 25 is 5. So we have 13 plus or minus 5 divided by 24. So that means I'm looking for angles whose sine values are 13 plus 5, 18 over 24. And I'm also looking for sine values that are 13 minus 5, which is 8 over 24. Now, when I'm looking at these numbers that we're trying to find the angles whose sine are these fractions, these are not fractions that we recognize. These are not ones that are special angles that we're supposed to just know off the top of our head. So what you're going to want to do here is use your calculator to find the angle who has a sine of, so this is inverse trig. We're asking our calculator, what is the angle that has a sine of 18 over 24? And over here, we're going to ask the calculator, what is an angle that has a sine of 8 over 24? So I would go to my calculator. Now, I've already done this. 18 over 24, when you take the inverse sine of it, is 48.59, rounding off to 2 decimal places. And taking the inverse sine of 8 over 24, you get 19.47. Notice when I show you the mode of this, I had my calculator in degree mode. Right here, you can see that. So these answers are in degrees, therefore they're going to need degree symbols when I write them down. So one of the answers for x was 48.59 degrees, and the other one was 19.47. Now again, going back to the original question, this was a problem that had no limits. So we are not just looking for the answers from the first go round. 48.59 is in the first quadrant. Because my sine value was positive, we should add on multiples of 360 to get all the rest of the answers. Every time we keep coming back around to the same spot, it's going to work. And the same thing for 19.7. We're going to add on multiples of 360 because they will also work. The only thing here is, if you remember your QRS, if you remember like what quadrants things are positive and negative in, you're going to recognize that quadrant 1 is not the only quadrant where sine values can be positive. Inverse sine is restricted to only giving you answers between negative 90 degrees and positive 90 degrees. So that's why our calculator is giving us this in quadrant 1. But there is another answer in quadrant 2 where sines are also positive, and the 48.59 degrees would become the reference angle, and you would have to subtract it from 180. So that angle is going to be 131.41 degrees plus multiples of 360. And we're going to have to do the same thing for 19.47. If 19.47 degrees works, then, because that's in quadrant 1, that's where sines are positive. There's another quadrant where sines are positive in quadrant 2. Our inverse sine could never give us those because it doesn't go that far. So if you subtract the 19.47 from 180, you're going to get 160.53 degrees and all of its coterminals as well. So there's a lot of answers here for this problem. All of these and all of these. Okay, our next example, number 3, is going to be an example of how to use factoring. This time, so you can see this is a problem about factoring. This time we do have limits. There are the limits right here. They'll usually put them right next to the problem if there's going to be limits. And a couple of things we can notice right away about the limits. They only want me to go from 0 to pi. So they're not really interested in coterminals being included because they only want answers from the first go around of the circle. And the other thing that this is telling us is that they do want our final answers to be in radians. So 0 to pi with no degree symbol on it. When I look at this, again, this is set up like a quadratic. We see a squared, we see a sine to the first power, and we see a constant. This one actually is pretty easy to factor. We should always, for quadratics, attempt to factor first. So the way that this would break down would be 2 sine of x and a regular sine of x. And then we want to think about two numbers that could multiply together to make -1, and also add together in the middle when you FOIL this out to give you a -1 coefficient in front of the middle term. So the two numbers that multiply together to make -1 are -1 and +1. And I just have to think about where I need them in this formula to make this work. The -1 has to be behind the regular sign, and the +1 has to be behind the 2 sine of x. That way, when I do my FOIL process, this would give me -2 sine of x, and this would give me +1 sine of x, which would give me the correct middle term that I'm looking for here. So this is the proper way to factor it. Like any other quadratic formula, once you have your quadratic factor, you want to make yourself a t-chart, and you want to set each one of the factors equal to 0. So sine of x minus 1 is going to equal 0, and 2 sine of x plus 1 should be equal to 0. On the right-hand side, if we move the 1 over to the other side, we're looking for angles whose sine values are 1. The only place on the unit circle where your sine value is 1 is at the very, very top, which is 90 degrees. So for this one, the answer I'm looking for is 90 degrees. For the left-hand side, in order to get sine by itself, we're going to have to move the 1 over to the other side by subtracting, and then divide both sides by 2. So we're looking for angles whose sine values are negative 1/2. Again, make yourself a chart to figure out where things are positive and negative. And since we're looking for a negative sine value that's not going to come from quadrants 1 or 2, we are expecting to get answers from quadrant 3 and from quadrant 4. These are the places where sine is negative. And the 1/2, you should recognize the reference angle for that is 30 degrees. So I want to be 30 degrees away from the x-axis in each of those quadrants 3 and 4. That would be 210 degrees and 330 degrees. So normally this is the point where you'd add on the coterminals. So if we go back and look at our limits, they only want the answers from the first full round of the circle. So 90 degrees, 210, and 330. And the other thing that they're looking for is for our final answer to be radians. So the last thing I have to do here is I have to convert 90 degrees into radians, which is pi over 2, 210 degrees into radians, which is 7 pi over 6, and 330 degrees into radians, which is 11 pi over 6. And there are your 3 answers. Those are our only 3 answers for this problem because this problem has limits. So last question that we're going to take a look at, last example. It's another example of using factoring. And this problem has no limits. So they're looking for all the answers, and we can be working in either radians or degrees. So most of us will probably choose to work in terms of degrees because it's easier. When you look at this equation, you see that we have terms on both sides of the equal sign. If you want to factor, or if you want to solve something, you really want it set equal to 0. So I'm going to take this entire term that's on the left-hand side and move it over to the right-hand side by subtracting. So you'll have cotangent of x times cosine squared of x minus 2 cotangent of x equals 0. You'll notice that there's a cotangent in both of these terms. So the kind of factoring technique that we're going to be using here is GCF, greatest common factoring. And we're going to take that one thing that both terms share, which is cotangent, and we're going to factor that out. So this is a very common factoring technique. Again, once you have your quadratic factors, you're going to be taking each one of the two terms and setting it equal to 0. So we're going to try to find out where cotangents are equal to 0, and we're going to try to find out where cosine squared x minus 2 would be equal to 0. These will be the solutions for our problem. Remember that cotangent of x is actually made of cosine over sine. So if you were to cross multiply this proportion, what's going to end up happening is you're really looking for places where your cosine value is equal to 0. Because 0 times anything is going to be 0 when you cross multiply in this direction for the sine times 0. So the cosine value on the unit circle is the x-coordinate, and the places where the x-coordinate is 0 is at both the top and the bottom of the unit circle. So those are going to be 90 degrees and 170 degrees. And because this problem had no limits, they do want the coterminals for this added on. So we'll put that plus n360s onto the back end of each one of these. And then we're going to go work on the right-hand side of this to find angles whose cosine squared is minus 2 equals 0. You're going to add the 2 to both sides. So we're looking for cosine squared x equals 2. We're going to take the square root of both sides. Remember that when you take a square root, that leaves you with a plus and a minus answer. So far, this looks pretty normal, except for one little thing. If you think about the cosine graph, the highest that the cosine graph ever goes up to is 1, and the lowest ever it goes down to is negative 1. The approximate value for the square root of 2 is 1.414. So what that means is we're looking for angles whose cosine values are bigger than what cosine can normally produce. That means this side of the equation has no solutions for x. There are no angles. If you tried this in the calculator, it would give you an error. If you did inverse cosine and you put the square root of 2 inside of it, it would give you an error because there are no angles that have cosine values that go that large. So that means that these answers back here that we got from the left-hand side would be the only answers to this problem. Thank you for watching this video. Go ahead and proceed and try homework number 112 after watching this. Ready to go.